Hi, I'm Alistair, and in this video I'm going to diagnose and fix a broken electronic device, specifically this Connect the Wires escape room prop controller. But even though this is just one example, the same processes and techniques I'm going to use apply to a very wide range of similar electronic devices. And if you learn to recognise and repair those faults when they happen, that's going to be a lot cheaper and quicker to fix them, and also a lot more environmentally friendly than just having to chuck this all away. So this prop was bought from an online supplier, but the first time the customer plugged it in, there was a puff of black smoke and it's never worked since. Now, the supplier wasn't helping to resolve the issue, so the person who bought it contacted me on Facebook and asked if I could repair it. Now, he sent it to me in the post, and once it arrived, the first step was to perform a quick visual inspection. I've never seen this prop before, so the only reference I had to go on was the description on the website. Now, on the front panel, there's two rows of sockets being held in with hot glue, and the wires going to each of those sockets are gathered into this bundle that goes to the controller board. On here you can see a couple of different modules, and also this separate board that has a button labelled Save on it on a little bit of perf board. But you don't have to look too hard to find an obvious problem right here. There's some bits of twisted metal sticking out and what looks like fluff surrounding them. It looks like something's exploded, and spoiler alert, that's exactly what's happened. Now, if you're experienced with electronics, you'll already know exactly what's happened here, but even if you're not, you'll probably agree that this doesn't look right. So the question becomes, what should we be looking at here? And this is where AI can be a really useful tool. I took a photo of the board and uploaded it to Google Lens, and this is what it said. It correctly identified that we were looking at a controller and some of the components on it. And if we focus in on where the damaged component was, which is this smaller blue board, we see it tells us it's an LM2596. And knowing a part number is a massive piece of information whenever you're trying to repair or debug anything. We can now do a search, and sure enough, we easily find a matching image. Now we can look at that image and compare it to the board that's blown, and we see that the precise component that's damaged is this cylindrical silver capacitor here. Of all electronic components, capacitors are always the ones that die in the most impressive ways. Now that's the only component that's obviously damaged, and if this were located in the middle of a much larger PCB, I'd probably just replace that one capacitor in isolation. But as it is, we can see that this whole power regulation board, this LM2596, is actually just a cheap removable module. You can get 5 of them for a £5, so it's easier to just replace the whole thing. And that means that if any of the other nearby components were also damaged, they'll get replaced too. Now, to remove the old regulator board, we need to desolder it. And to desolder a component, I'm going to use some solder wick. This is a kind of copper braid which you place over a solder joint and then touch your soldering iron onto the top of it. It will melt the solder underneath, which will get wicked up into the braid. And you repeat this on all of the solder contact points, and then you can lift a component off. Now, before installing the replacement, we need to do a little bit of preparation first, because one important thing to note is that these are variable voltage regulators. This little brass screw on the top of the blue potentiometer allows you to vary the output from the terminals here. And so before installing this into the board, I need to make sure that that is set correctly. So what I'm going to do is I'm going to connect 12 volts via these crocodile clips onto the inside of the terminal. And I know that 12 volt was the power supply that was being used to power this unit. Let's obviously turn it on. And now what I'm going to do is I'm going to got my multimeter set to a voltage setting. I'm just going to put the probes onto the output terminals there. So you see at the moment it's outputting 11 volts of its 12 volt input, and if I was to install that onto the board as it is, that would almost certainly damage the rest of the components. That might even be what happened last time. So now I'm just going to turn this brass screw And what I find with these is you have to turn them quite a long way and nothing happens at all. and then all of a sudden, hopefully, we'll see that voltage start to go down. So I'm turning it anti-clockwise to reduce the voltage. And what I want to do is to get that value down to 5 volts, which is going to be the correct output to power the components on the rest of the board. Now I've done that, what I can do is put a little blob of glue onto the top of that screw there to prevent it accidentally being turned again, and know that the output it's set to is correct. And now we can install that module into the place we removed the old board from. So now that we've replaced the obviously damaged part, we can continue the visual inspection of the rest of the board. You can do this with a magnifying glass, or if you've got very good eyesight, just look at it yourself, or you can use a desktop microscope like this. And what we're looking for is things like loose wires, cracked joints, perhaps 2 touching cables that might cause a short, or a blob of solder that's spread from one pad to another. And once I was happy that everything looked okay, it was time to try powering it up. And this got off to quite an encouraging start. The LEDs on the front light up, nothing blew up, and this light comes on. So this is a 12-volt lamp which I've connected to the output socket. Normally this would be where you attach a mag lock, but you can't tell from looking at a mag lock whether it's energized or not. So if you attach a lamp instead, you can tell at a glance. When it's lit, that would mean the mag lock is closed, and when the light goes off, the mag lock would be released. Now, unfortunately, it's at this point that things start to go a bit downhill, because besides flashing this red animation pattern on the front LEDs, nothing really seems to happen. I tried plugging all the cables in and removing them, and there was no obvious feedback. I tried pressing the save button on the side, and that didn't seem to store values. I reset the controller a few times, and then I noticed that on occasion the light would turn off just randomly, or when I touched a particular connector. So clearly something's not right, and we need to do a little bit more investigation. What we'd really like to do is to be able to see inside what's going on inside the controller. You'll know that in most of my projects I use print statements throughout the code to display the state of the program or the value of different input and output variables. And I wondered, well, perhaps this controller does the same. Now you might remember that Google Lens told us that the controller on this board is an Arduino Mini. And if you're familiar with using Arduinos, you'll know that you can plug a USB cable into the board and open up the Arduino serial monitor to view the output of any messages sent. Now the Arduino Mini uses exactly the same processor as a Uno or Nano, but it doesn't have an onboard USB serial chip. So to view those messages, we need to use an external one, like this FT232 programmer. This connects to the ground, VCC, transmit and receive pins on the edge of the controller board here. And then if I plug the USB cable in, we'll be able to see any serial messages that the code is outputting. You can see I get start, init and save messages coming up as soon as the code starts, but unfortunately these are the only messages I can get it to output. And of course I don't know what messages are meant to be sent, whether anything should be reported when a cable is plugged in or out, for example. And even though the program seems to be running okay, it's generating these messages and it's lighting up the LEDs, what might have happened is that when the capacitor blew up, it caused some internal damage. So it would be good to upload a diagnostic sketch onto the processor that printed out the values read at all the input pins. Now if I do that, it's going to erase the program that's currently there, and there wouldn't be any way to restore that. And even though that's not behaving correctly at the moment anyway, I'm always very reluctant to overwrite any code or commit to any irreversible modifications unless they're a last resort. So the next step is to try to take a backup of the code that's currently on the chip in the hope that I can recover it if necessary later. Now, although you can upload a new sketch via a serial programmer like this, you can't use it to download the program from the chip. To do that, we need to use ICSP, which is where you program the chip via an SPI interface from another device, typically another Arduino, which is running a sketch called Arduino as ISP, which is one of the examples provided with the Arduino IDE. Now, many Arduino models have the ICSP pins broken out in a 2x3 header, which has got the clock, MISO, MOSI, 5V ground and reset pins required for SPI. And those are the 6 connections you need to make between the programmer and the target board. You mostly just connect these to the corresponding pins on both boards. However, don't wire the 2 reset pins to each other. And having praised AI for correctly helping to identify the LN2596 module earlier, on this occasion it gets it completely wrong. The reset pin is brought to ground to reset the controller, and you keep it held low while reading or writing to the target device using the SPI pins. So if you were to connect both reset pins together, then as soon as you brought it to ground, it would reset both devices and also stop the programmer Arduino from running, so it's not going to be able to read the flash code anymore. So you connect the reset pin on the target board only to a regular GPIO pin on the programmer board, such as pin 10. Then the programmer can send the reset signal by writing a high or low signal to that pin and control the target MCU. So that's the hardware setup. Now, the Arduino IDE doesn't include a command to download the code from a connected device over ICSP. But AVRdude, which is the command line program which Arduino runs behind the scenes, does. So this is the command to read the code from the flash memory of the controller and dump it to a backup file. So this is the main program code, the compiled Arduino sketch that was uploaded onto this device. Now, I assume that the save button stores the solution to the puzzle in a way that persists even when the power is turned off to the controller. So that means it must write to the EEPROM memory instead of the flash memory. And we can also read and dump a backup copy of the EEPROM using this AVRdude command. And now that I've downloaded a copy of the flash memory of the chip and also the saved configuration from the EEPROM, I can upload a new sketch onto the controller without worrying about losing the original. I can always restore the functionality it had by just copying that backup file back across again. So I'm going to upload a new sketch that displays on the serial monitor whenever a wire is connected or removed, or when a pair of sockets have been wired together. And to detect that, I need to know which GPIO pins on the controller are used for each of these sockets. Now you can do that by visually following the copper traces on the PCB and through the cables, or you can do it using a multimeter. Now some multimeters have a dedicated continuity mode, but you don't need that. I've just got a basic multimeter here set to resistance testing mode. So this is going to display the resistance measured between the 2 probes. If it shows the value 1, that means that there's no direct electrical connection between them at all. Then I'm going to hold the black probe on one of the sockets on the front panel and then touch the tip of the red probe onto the top of each of the GPIO pins on the Mini in turn. Most of them don't do anything. But when I touch this pin, you can see that the reading on the multimeter goes down to 0. This is GPIO pin 13 according to the label on the board. So if the resistance is close to 0, that means that this socket is directly connected to that pin. And now what I'm going to do is take a white marker pen and just write that pin number next to the socket. And then I'm going to repeat that for each of the other sockets and pins on the controller until I get a complete pin map. I also want to know when the save button has been pressed, so I'm going to do exactly the same thing to identify the GPIO connected to the wire that leads to the perf board with that save button on it. And once I'd identified the corresponding GPIO pins and labelled each socket, I also put those values into arrays in my diagnostic sketch, one array each for the top and bottom rows of pins. And then I connected the FTDI interface again and opened a serial monitor so that I could print out the raw values that were being read at each of those pins. But what I found was that the readings were very erratic. So that meant it was time to break out the multimeter again. So last time I used this to check for continuity between the sockets on the front panel of the prop and the pins on the board here to find out which of the GPIO outputs corresponded to which wire. But what I hadn't done was use this to check for continuity between different points on the board itself. So for example, if I hold one prop against pin 2 and another on pin 3, you'll see that I'm still detecting a resistance of 1 or infinite resistance between them. So those 2 points are not electrically connected. And that's what you'd expect on a board like this, where I've got no other components attached, it's not powered up. You would expect each of the GPIO pins to be completely independent and isolated from each other. But watch what happens when I put my probes against GPIO pins 7 and 8. You'll see that I'm now detecting a resistance between them of only 72 ohms. And that is not right and not what you'd expect. These should all be independent and completely isolated from each other. Now, just to see, I then tried measuring that same value directly on the pins of the processor in the middle here. And you see I'm getting exactly the same reading when I take it at the processor itself. So this suggests that perhaps there has been some damage to the central processor chip here, and that needs to get replaced, or in all likelihood it's much easier just to replace the complete Arduino Nano board. So now the next step was to replace the Pro Mini controller completely with a fresh one. Unfortunately, because I had already downloaded the code from the faulty chip using the ICSP interface, I was able to copy that directly onto the new board, and finally the prop worked as expected. Now the ironic thing is that now that I've already had to investigate and document the layout of the hardware to perform the diagnostic checks, the value in restoring the original code is actually a little bit pointless. I've already written my own Connect the Wires project some time ago, so I simply updated that with the new pin map. And that meant I knew exactly how the logic worked, I could change the LED animations to provide better feedback, and customise the way in which the solution was saved. So now what I've ended up with is a sort of prop of Theseus. I've replaced most of the active components on it, the power regulator board, the controller board, and I'm now using completely new code. It's really only the front panel that has remained unchanged. So is it still the same prop? I don't really know. So that's about it for this video, and what has it taught us? Well, firstly, some people mistakenly think that buying an off-the-shelf prop controller means you're going to get higher quality than building your own using an Arduino. But you don't. As I've shown, inside they're often built using exactly the same components. They're held together with the same hot glue, and they fail in the same ways. So if you build your own props, be proud of your creations. They are just as good, or often better, than many things that people are selling for hundreds or thousands of dollars. And secondly, things do fail, and knowing techniques like how to use a multimeter, how to desolder a component, or how to download and clone code onto a replacement chip can help you deal with those failures. Now, as it happens, on this occasion, it would have been better if I'd just thrown the whole board away and replaced it, but I guess I only knew that was necessary after having gone through various steps along the way, which could have resolved the problem quicker and easier. So I hope you found this summary useful. If you'd like more information on any of the tools or processes I used, or if you want to discuss anything else about the technology projects in this channel, or perhaps share something that you're making, please do check out my Patreon or the Discord server link in the description below. Other than that, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.